In this lecture, we are going to build machine learning solutions for real-world datasets. So let's get started. Now first, we'll see the bike sharing demand prediction using decision trees and random forest regression. In this section, apparently we are having a regression problem in front of us. So we are going to explore the dataset and identify the problem. And then we are going to talk about the algorithms that we are going to use here, that is decision trees and random forests. And then we will see some feature analysis, some feature engineering, followed by the implementation of our solution and analyzing the results. So let's start by exploring the dataset and identifying the problems. So we are going to see bike sharing demand dataset, and we are going to see what is our goal using this dataset. So bike sharing demand data is quite popular dataset. Bike sharing systems are means of renting bikes where the process of obtaining membership, that is rental and bike return, is automated via network of key solutions throughout the city. Using these systems, people are able to rent a bike at one location and return it to a different one. Currently, there are over 500 bike sharing programs around the world. It is interesting, the data generated from these systems are very attractive for researchers because everything is recorded. Things like the duration of travel, departure location, arrival location, and the time elapsed are all things that are recorded. And this dataset, we are not only having this information, but we are also having the weather information for every single day and the hour, which you will see later. Now Kaggle had hosted this competition for machine learning community to use it for fun and practice, and the data itself was provided by Hadi Funny Talk using the data from Capital Bikeshare from Washington DC. UCI Machine Learning Repository is also hosting this dataset. And here is the paper that you should definitely check out if you are interested in learning more about this dataset. So as we mentioned before, this is a regression problem because we are trying to figure out what is the number of bikes that we will be needing every day in the city. And the data itself contains 14 independent variables. And our main goal is to get the count of rentals as output of our machine learning model. The data itself is containing two CSV files, r.csv and day.csv. But we'll be only using the r.csv file, and it contains hourly samples for our approach. Now here is how the dataset looks like. We are having day, time, season, year, month, hour, and we are having the distinction that was it a holiday or was it a weekday or was it working late. Also, we are having some weather information like what kind of weather was that day, what was the temperature and what was the temperature feeling, as well as the humidity and wind speed. And finally, the number of casual rentals and number of registered rentals. And the final column, which is a count of total rentals in that day, which is our goal, and we want to figure out what is the number of rentals that was happening in a certain hour. So next, we are going to see what are decision trees and how we can use them. Also, we are going to see how the random forest algorithm works in brief. So we are going to take a look at regression decision trees and regression random forests. And what kind of problems are they trying to solve and what is their function. So it is important to notice here that I will be talking about regression decision trees and regression decision forests and regression random forests. And we have already seen the classification version of these algorithms. So let's start with decision trees and what are they and what are the problems that they are trying to solve. So let's start with decision trees and look at what are they and what are the problems that they are trying to solve. So basically, as I've mentioned before, they are covering both classification and regression, and similar principles apply, but there are certain differences of course. And basically they are used visually, and explicitly it will represent decisions and decision making, which is very good for data mining, and basically it is good for data analysis. They are having these conditions what we call internal nodes, based on which a tree splits into different branches and which we call edges. And in the end branch that does not split anymore, it's called a decision or a leaf. This is how that would look like. It's a pretty straightforward approach. So we are asking whether a certain condition for our data, for example, we are asking if our x is larger than, let's say, 2, and if it's not, then we are going to delete one where we have certain decision. We say, okay, our output data will be this much. Otherwise, we go to condition 2 where we ask, is our x value, for example, larger than 7, and if it's not, then we are having all the terminal leaf to where we say output value is then this much. Otherwise, we are going to determine all leaf tree where we say, for example, output value working or something like that. So what we basically ask is, our input data having some attributes, and does it apply to a certain condition? If it has, we are having some decisions and we are making decisions regarding the output. Otherwise, we are going to the second condition and so on. Now these decision trees are pretty simple and they are good because we don't have to apply too much data pre-processing. Everything is handled inside of the decision trees themselves. So how that would look like on some data set? For example, if we have two input attributes x1 and x2, and imagine that our output is actually a third dimension to this chart. So imagine that we are having a y-axis which is going through your screen into the 0 point. So you can see that we are having certain splits, and these splits are actually our conditions. Looking at our data, and we see certain things apply for that data that have x2 value of less than this number here. We can imagine it, this number is 10. So we say certain things apply to the data that is having x2 smaller than 10, and then certain things apply for the data that has x2 larger than 10, and then this split is a certain condition and we are having different conditions here. So when we split our data like this, we are having these sections that you can see between those splits and between our axes. We can say that for this part here, we are applying for all these data points, that is, we are applying a certain regression model and we get a certain value for all of them, and then we average out that value, or basically we apply the regression algorithm to this one and this one at this point and this point, and then we say, okay, average value of these outputs, this one, and then if we get a new data point that is somewhere over here, let's say we take the y value that we learned. So you see that basically using this we are having an average value which might be, let's say, correct, but our whole ballpark might be better because we might have some outliers here and they will be averaged out. They will not affect our final calculation, and that is one cool thing about decision trees. So what is ensemble learning and random forest? Well, ensemble learning is when we take multiple algorithms, or one algorithm actually, and apply it multiple times. And random forest is this type of ensemble learning where we actually use decision trees to make an ensemble. So our algorithm is actually a decision tree algorithm and we apply it several times, and that is how you get random forests. Or to be more exact, we pick random n data points from the data training set and then we build a decision tree associated with these n data points. Once that is done, we choose a number of trees that you want to build and we repeat those first two steps. So first thing that we do is basically we pick up some random data points and then we build the decision tree associated to that n data points, and then we repeat this process using different decision trees, meaning different conditions, and then we get different results. And finally, when we are done for each new data point, we make each one of these trees predict the output and then we take the average. So instead of having one decision tree that is averaging all that out, we have multiple decision trees. And what this is helping us with is actually the decision trees have this affinity towards overfitting because they might be too attached to the training data. So in a way, they learn everything by heart and we want to escape that. So we don't want that to happen. And the random forests actually help us with that because we build multiple decision trees for each new point. And we basically run all those decision trees and we get a certain value. And yeah, that's pretty much what we are doing with random forests. And we have seen this process in the earlier lecture too. And then this is how it looks. So basically we are having multiple decision trees and we are getting the certain outputs for each of these decision trees. And then we eventually average that output and hopefully that is how we get a better value than we expected. So that would be all for our decision trees and random forest approach that we are going to use to solve our bike sharing problem. So next we are going to do some feature analysis and we are going to dive even deeper into the dataset, and then we are going to do some feature engineering, and basically we are going to see that we really don't need some of those features, or to be more exact, we don't need them to have them in our model. So here we are in our Jupyter notebook and we are first going to detect if there is any missing data in our dataset. Then we are going to do the outlier detection and then we will also perform a correlation analysis. So here we are, and as I have mentioned before, we are only going to use the RLE examples. So thus we are importing only the r.csv file. So now in cell 2, first we are going to import the necessary libraries. I have imported calendar, numpy, pandas, seaborn, missing number, date time, matplotlib and warnings. And basically we are going to use each of these for a different purpose. And in cell 3, we'll start by importing our data first, and we are going to use the readcsv function so that we can just read our file, and then we will move on to see if there is any missing data in our dataset. So now in cell 4, let's just modify this data a little bit so that it will be easier for future analysis. So the first thing that I've done here is I've created a season map, and because season is recorded as an integer, and if you want to analyze the dataset in an intuitive way, you might find it difficult to analyze it with numbers. So to prettify the data and to analyze it intuitive way, I have done the reverse encoding. So if numbers are provided in the dataset, I have encoded them as strings. So here we have the season and then we have the weather. So once that's done, now we finally split up our data from the DTE day, and then we get the weekend and we get the season with the season map and we get the weather from the weather map. So that's something that we have done, and now let's check that what we have in our dataset using .head. So as you can see here, this is our data. So as you can see here that we are still having this date column over here, and we are also having season, year, month, hour, holiday, weekday and so on. And we are also interested in this count number, and that is pretty much how it looks like. So now coming down to cell 5, first I have separated the category variables that I am interested in. So basically I am interested in hour, weekday, month, season, weather, holiday and working day, and then I have changed the data types of those columns to category. Also, I have dropped the DTE day column since we have already extracted the necessary columns out of it and it's no longer needed. So here I have dropped the DTE day. Now coming to cell 6, we will see if there is any missing data because we are having more than 37,000 records, so it will be hard to look for it manually. And for seeing the missing data, we are going to use this missing number library, and using this matrix function from the missing number library, we can see here that basically there is no missing data. I would have other indicators here that would say to me that there is missing data for each of these columns in our dataset if there were to be any missing values. But since we don't have any missing values, that is great news. Now this means that we don't have to manipulate our data anymore, and we will use it as it is. So we don't need to do any kind of averaging or something like that, and we can directly jump on to outlier detection. Now before I proceed, let me say a few things about outliers. So outliers are basically observations that appear to be far away and divergent from an overall pattern in a sample. And there are two types of outliers, univariate and multivariate. So univariate can be detected when you look at the distribution of a single variable, while multivariate outliers are outliers in n-dimensional space, and in order to find them, you will have to look at the distribution in multi-dimensions of multiple variables. So now in cell 7, let's see how we are going to do this in our data that we are having here. So I have added this code basically, and I am using the Seaborn module to plot the distribution of the data. So how does that look like? And here it is. So it's pretty colorful, but actually this is the distribution of our data, and most of our values are actually between two values here, but these values are representing the outliers, and they are representing something that introduces non-linearity into our dataset. So as you can see here that we are having quite a lot of them, and you can see here that these dots are connected together. And if we take a look at the other plots that we are having, we actually used distribution of counts per season. So this is that plot. So our counts are distributed by season. So we have fall, spring, summer and winter. So if we take a look at spring, for example, we are having this much outliers, but we can also see that springtime is the lowest when it comes to renting of the bikes, and the fall, summer and winter are somewhat more popular. Now here we can see the count per hour distribution, and here you can see that there are a lot of outliers in the middle of the day and late and early morning, and we can see here that we are having a lot of outliers when we are talking about working day or normal day. So right now for this demo we are not going to remove any outliers, but if you want you can remove them, and then for your distribution the linearity will be higher. Now coming to cell 8, let's see the correlation analysis, and here we will basically check what is the correlation between our features and basically how they are connected to our target variable of count, and are they going to affect our count in any way that we don't want it to. So here is what we are going to do, and I have made this correlation map with the features that I am interested in. So basically I am interested in temperature, atemp, casual, registered, humidity, wind speed and count. So basically I want to check if my count is relying too much on any one of these features, or is any of the features actually having too low of an effect on the count itself. And this will help me to determine if I can remove any features from my dataset and make this data easier for our model to work with. And as you can see here, we've got a pretty mix, which is that we are having all of the features here, and so we want to observe how the count is related to the other features. And we can see that wind speed is having too low of an effect on the count itself, but we can see here that registered is actually having a very high correlation with the count. And this means that we need to remove this registered feature from our dataset, because it will give us data leakage, which is something that happens to a model when you are having these kind of variables that are affecting the final outcome too much. So this will result in a model that will be invalid for perhaps highly optimistic predictions, and so we will remove this feature from our dataset. And we will also remove casual, because casual and registered are highly correlated features between each other, and we want to remove them. So that is what we observe from our correlation analysis. So we learn that we are having a lot of outliers, and we don't want to fiddle around with this dataset anymore, and we need to remove the two highly correlated features so our model won't be invalid. Now we are going to do quite a few things, but they will all be around implementing random forest regressors. So we are going to prepare our data a little bit, so it will be prepared for our model to be processed. And if you remember, we said that we will remove some of the features and then we will change some of the existing features as well. So let's do that. So in cell 9, I will read in my dataset again, and you can see here that we are having all our features that we had talked about, and if you remember, we said that we will remove casual and registered. And we will remove count as well, because the count is something that we want to train our model on. And we will modify this date time a little bit, because I would like it to be in proper data type. So first, let's separate the date, and then I've created a new column called date and weekday. And now let's create categorical features, and let's define which of the features we are going to remove. So here it is. Our categorical features include season, holiday, weather, weekday, etc. And then in our numerical features we have temperature, humidity, wind speed, etc. Also we want to drop the features casual, count, DT, day, etc. So we have made a list of all these features and then we will drop them. And you might be wondering that why did we create it in the first place if we had to drop it later on? Well, we needed these features so that we can check the week date, because that will be important for our dataset. So we have kind of extracted all the necessary information from this feature so that we can remove it. And yes, we are removing the count because we actually want to predict it. And we are removing causal and registered columns because those two have shown high correlation to the count. Alright, so now we come to cell 10, and you might be wondering that I haven't dropped my features yet. Well, the reason is that I want to extract this count in a separate variable, and so I can have it as an R output and leave data matrix with only inputs. I'm going to first extract that, and then I'm going to drop the features. And finally, I will split this data into training and test set. So the first thing that I've done here is that sorted count values by this DTE day, so it will be properly aligned. And then I said that my Y variable will be data of count. So this will be our output. And now we'll drop all the features that we have defined in these drop features. And then I used train test split function from this model selection library to split the data into training and testing. So now in cell 11, finally we are going to create the regressor using scikit-learn and make some predictions. So here we have basically imported random forest regressor from the sklearn ensemble library, and then I have created a model using 500 trees. And now remember how we had talked in the slides about defining the number of trees for each forest, and then we use the fit method to xtrain and ytrain, and then we have created our predictions. So now in cell 12 we are going to analyze the results that we got from our implementation. Also, we will be implementing the root mean square log error, and we will find out which variables had the biggest effect on our result. So before we continue, let's see what RMSLE is. So it's actually the root mean square logarithmic function, and we will be using it for calculating the error between predicted value and the actual value, of course. And this can be used when you want to penalize underestimates more than our overestimates. And here is the function that it uses. And yeah, basically what we want to do is give some favor to the overestimates over the underestimates. And let's see how we can do that. So the first thing that I'm going to do here is, actually I'm going to define the function, and then we will calculate the root mean squared logarithmic error for us. And here it is, and I will call this function on our predictions and on our y-test. So what we can see here is the value that we get is 0.28. So what this value means, it's not that bad, but it's not that good either. So let's move to cell 13, and here what we'll do is we'll see what is the feature that affected our model the most and our predictions the most. So here is the part of the code that we will use. We will use the pandas again, and we will take the columns from the xtrain, set their features and coefficients from the model itself, that is feature importances. So basically we are having in our model already these statistics that can help us regarding which feature had the most important effect on our model. And then we'll use matplotlib to make the graph here. So in this plot here you can see that the feature that had the most effect on our prediction was actually the R feature, and then instant and temperature and working day and so on. So this really helps us. What if we want to improve our model and we can say, okay, maybe we can actually, look at these features for which we have good results here, and we can somehow improve our model or remove some of the features and then make our model better using that. So that is it from this section, and in this section we had a chance to explore bike sharing demand dataset, and we saw how decision trees and random forest algorithms work. Then we did a little bit of feature engineering and we saw which features we should remove from our data. And then of course we built our model using scikit-learn, and we finally analyzed our results and displayed which feature had the most effect on our results. Next, we are going to do some classification and we are going to talk about heart disease predictions, and for that we will be using the support vector machines. So in this section, we will see how to make heart disease predictions with support vector machines. Now in this section, we will follow pretty much the standard path that we saw in the previous section. First, we will explore the dataset and identify the problem. After that, we are going to talk about support vector machines which we are using for solving this problem. And then we will do some feature analysis and feature engineering. And finally, we will do the implementation using the theory that we will be seeing. And then we will analyze the result and see how we can get better results by changing a few things. So let's start by exploring the dataset and identifying the problem. Here we will see what is happening in a heart disease dataset, and then we are going to see what kind of problems are we actually trying to solve. So heart disease data is collected from 3 hospital systems, from Cleveland, from Hungary and from Switzerland. This database contains 76 attributes, but all publisher experiments refer to use a subset of 14 of them. And that is what we are going to do as well. And we are going to use just 14 attributes, meaning 14 features. The goal field refers to the presence of the heart disease in the patients. It's an integer value from 0, no presence, to 4. The goal of our solution would be to predict this value based on other 13 features. It is important to note that names and social security numbers of the patients were removed from the database and replaced with dummy values. So in this concrete example, we will use classification approach. So we will have to classify, do we have a heart disease or we don't. And as I mentioned previously, there are 14 features. 13 of them are independent variables which will be the inputs of our model. And then we have one target variable. The dataset is containing from the 3 files, and the first one is cleveland.csv file, then we have the hungary.csv file, and finally we have a third switzerland.csv file. And we will be combining those 3 files into one big dataset, and we will see how we are going to do that pretty soon. And here is an example of how our dataset is looking like. So basically here you can see we have 13 features varying from the age to the cholesterol levels and pressure. And finally we are having num, which is our final column, and it has values from 0 to 4. So next we are going to see what are support vector machines and how they function, because we will use them to implement our solution. So now we are going to take a look at how the support vector machine algorithm works, and we will see what is a kernel trick. Also we will see how this kernel trick can be helpful to us, and also we will see what kind of problems support vector machines can solve in general. So support vector machines are covering both classification and regression, but we are going to use it for classification. A support vector machine model or a SVM model is a representation of the examples as points in space mapped so that examples of the separate categories are divided by the clear gap that is as wide as possible. Now what does this mean? So basically we are having these 2 types of data. You can see that we are having again x1 and x2 axis. So those are our 2 features, and we are having red dots and these blue crosses. So they represent 2 types of classes based on the attributes of x1 and x2. Now we can put our model, that is some line which will separate them like this, and That way, if new data comes in based on values of x1 and x2, we will know in which side we will put it and we will know which type of class does it belong to. But the problem is that this line can look very differently. Basically, you can put the line through the data any way you like, and then the new data will be in a different place than it is in this example. So our mathematical model can look like this, or it can even look like this. So our mathematical model will keep changing because there are many ways in which the line can classify the red dots and blue crosses. Now, this is not the best case, of course. So here is what support vector machines are actually doing. It is taking into consideration these 2 points which are closest to each other. So the difference between this and this point is much less obviously than, let's say, this and this point. So if we take a look at this point and we see that the values for this point are pretty clear, we are certain that this is a blue cross, and for this one we will take a look into the data the same way and say that this is pretty clear to us that this is actually a red circle. But what about these two? These two have attributes which are not that far away from each other, and that is exactly what support vector machines is doing. It is taking these two values and it is calculating something that's called maximum margin, and this maximum margin is actually a hyperplane. Don't get confused by that fancy term, but imagine it as it goes through your screen as a normal going to your screen on this line. And why is that called support vectors? Because in the three-dimensional space, in a mathematical vector space, these 2 points are vectors. And why this algorithm is so powerful? Well, basically, instead of taking these certain points and then when a new value comes in, it compares them and then knows in which class they should be used. This algorithm is basically creating the gap, and then we saw when the new value comes in, it will know which way it should go comparing it to these support vectors which are supporting this maximum margin. And that is why support vector machines are very cool, and this is why we can use them for both regression and classification. But take a look at this example. Through this, there is no way that you can put a mathematical model like a straight line or even a polynomial line would not help in this case. So how do we solve this? Well, in this case, we are using something that's called the kernel trick, and this adds another dimension to our plane. So basically, here imagine that you are having a third dimension coming out from your screen, and it uses this to add linearity to our system. Now for this example, we will be using a radial basis transfer function, which is a Gaussian function pretty much. You can see this curve here, and you have seen this a lot of times in your life. So imagine this 3D shape coming out of your screen, and all the values that are 0 for this will be blue crosses, and not zeros will be actually red circles. So that would be all about support vector machines. And now you have learned how support vector machines are working and what is the kernel trick. So next we will do some feature analysis and some feature engineering on our dataset, and then we will be actually using the support vector machines, and we will try out different kernel tricks, different kernel functions, and see which one is the best for our classification example. So now we come to our Jupyter notebook, and we are going to analyze our heart disease dataset, and we will see if we have any missing data or if we have any class imbalance. And we are also going to do the outlier detection and correlation analysis. So in cell 1, we have imported our libraries like NumPy, Pandas, Missing Number, Seaborn, and Matplotlib. And from pre-processing, I will import Normalize, Imputer, and Standard Scaler. You will see that how I will use each of these. And from model selection, I have imported Train Test Split, and you are already familiar with this library. So now I am also going to use SVM, which we will be using for implementation of our model. Finally, I am going to use accuracy score, which will give us the metrics for our classification label. So now coming to cell 2, here we first load our datasets from the files, and we have also defined the features of our data because our data set does not have any headers in the CSV file. So here we are basically defining our features using the features variable. Then we will be loading the cleveland.csv, hungary.csv and switzerland.csv files. And we are saying that the names are the features that we have defined in this variable. Now in cell 3, we will combine these data sets. So we are creating a temporary variable called datatemp, and here we are defining it as an array of the data that we have just loaded. And finally, we are using the concat function of pandas to concatenate all of this into one data set. So we are combining 303 plus 294 plus 123 rows, and that is actually we get 720 samples. So here they are all combined in one big data set. Now if we check using the .tail function the last few rows of our data, we can see here that we have some question marks. And so what we can see here is that we are getting some question marks, and what we are guessing is actually that these are not the correct ones. So in cell 4, we will need to replace these question marks with some proper values, and we need to replace them with something valuable like np.nan. Now np.nan just means from NumPy we will be using not a number, and then we will later on see how to handle it. So here we will just drop CA, slope and PHAL features because we don't actually need them, and then we will replace the question marks with some values. So now once I have done that, in cell 5 we will be handling the missing values. So missing number library provides a plot, and we can see here that we have missing data, and this is because we have replaced all the question marks with nan values. So now in cell 6, let's draw this data and see what the outlier situation is here. So we will check the distribution of the data using box plots, and we will have a look at the outliers. But what is more important here in this picture is that we can see we are having a class imbalance. Basically, we are having more data here, and you can also see that the values are not up to scale. Some values are lower and some are very high. So there is clearly a scale difference here between the features, and we are having a few outliers here and here. But if we take a look at the whole distribution of heart disease, we can see that here we get only a couple of outliers. Then again, if we take a look at the heart disease by age, we can see that we are having more data for older patients. So we can say that these problems actually are related more to older people. But we are also seeing here peaks for the age of 50 years or something like that. And then finally, we are going to take a look at the heart disease by gender. And basically, where zeros are females and ones are males. And we can see here that we are having more male data compared to the female data. So now in cell 7, let's do a correlation analysis, and maybe we can detect if there are any features that we need to remove. So here is the code, and this is the standard code we will be using for the correlation heat map. So a note here that heart disease is not affected by these features too much, so we don't have to remove any of the variables. So that's actually good. So now we have basically explored our data, and we saw that we have some missing information, and we decided that we are going to drop 3 features actually because they are irrelevant and there is not enough information in them. And then we also decided that we are not going to drop any additional features because from the correlation analysis we realized that it's alright to have these features and none of it is affecting our datasets too much. And yeah, that's pretty much it. So now we are going to implement the solution on heart disease dataset using support vector machines. So let's jump right into it. So we realized here that we don't need these 3 features because they are missing too much information and they are irrelevant. But apart from them, we were also having some missing information in other features as well. So in cell 8, we will replace those missing information with something concrete. So let's see how to do that. So here we are going to use imputer, and this will basically change the nan values into something else. And we are defining it here and we are saying that missing values need to be replaced are nans, and then the strategy for replacing them, we are saying that we will impute by mean. And what this means that the imputer will get the mean of the whole column and it will replace the nan values with the value of that mean. So finally, we are getting imputed data. Then by using fit and transform, we pass the data in here and we will get the imputed data. And if you do a dot tail, you will see that there are no nans in the data. So now in cell 9, let's split the data into training set and testing. And we are already familiar with this. So we are passing on the imputed data without the last column, that is our output. And that we are passing here as the second attribute in this method. So you can see that here I am using this, which is saying everything except the last column, and this one is just saying that give me the last column. So I am using the imputed data and I will create xtrain and xtest. So you will see that now I am having xtrain and xtest and also ytrain and ytest. Now when we get our training and testing data, we can actually scale it. If you remember, we had a problem of class imbalance. Basically, we are having some values in one scale and other in another scale. This would hamper our model performance, and this is why we are using standard scaler. So in return, when we take a look at our training later, we will see that now it is basically from minus some value to plus some value, but they are all somewhere in between, let's say minus 3 to 3 something values. So all of the values are in same scale and we are not having a problem with unscaled data anymore. So in cell 10, we can finally go and build our model. So now we are using SVM and SVC class, and we can see here that we are saying that we want to use this kernel as RBF. So this kernel can be changed from linear or poly or so on and so forth, and we will see this later on how it will impact our results. And then we are using classifier.fit to fit this xtrain and ytrain data to it. And then we are using predict method on our xtest. So now we are having a variable predictions here, and that is having our predicted data from 0 to 4. So now if you will view the predictions and compare it to the test data, you can see that we are having some good predictions and some are very bad. So you will see the accuracy of this model shortly, but what I wanted to say here is that changing the kernel will basically give us different opportunities and we can experiment a bit with these different kernels. So now we are going to see the accuracy score and we are going to play around with the SVM kernels. So in cell 11, I am going to use the accuracy score method and I am going to pass the ytest and predictions that we had actually got. And if you look at the accuracy, we get an accuracy of 65%. So that's not so good, but it's not that bad either. It could be a little bit better, but what that 65% is telling me that basically in more than half times I will get the right and correct results. Also, it is telling me that I didn't use any unnecessary features and I got some results which can be used. So what I can do here is that I will try to change the kernel from RBF to linear and then we will see if we can possibly get any better results. So as I mentioned previously, I can use a linear kernel here and if I run it, I would get a different accuracy. So here you can see that I got an accuracy of 62%. So now in cell 12, you can see the accuracy that I got 62% using linear kernel, and this is less than the previous accuracy which I had got when I had used RBF. So this is not good and it didn't give me any better results. Now in cell 13, I will try to use the sigmoid and this time I get an accuracy of about 62.9%. Now this is better than the linear kernel, but it's not better than the RBF. So now in cell 14, let's try out the polynomial kernel and we'll check if we can get something better. So you can see here that it is the same as sigmoid, but still pretty much under the RBF. So it turns out that our data is actually pretty much similar to the ones that we saw on the slide, that it is nonlinear and we should use the RBF function because with that we get an accuracy of 65%. And that will be it from this section. So here we saw that the first thing we did was exploring our heart disease dataset, and then we learned all about the support vector machines. We did some feature engineering on our dataset, and finally we built our model using scikit-learn, and then we analyzed and displayed our results. Now let's move on to making poker hand predictions using k-means clustering algorithm. Now in this last section, we will take a look at poker hand predictions using k-means clustering. So here we are going to take a look at one very interesting example, and we will try to predict what do we have in a poker hand, which is of course something that no one can do. But we are going to approach this data and see what we will get when we use k-means clustering. To sum it up in this section, we are first going to explore the dataset and identify the problem. And then we will see what k-means clustering algorithm is all about, and then we are going to do some feature analysis and feature engineering before heading on to the implementation and analysis of our results. So let's explore the poker hand dataset, and we are going to try to examine what kind of problem do we have in our hands when we are using this dataset. So this dataset basically contains simple data. Each record of this dataset is an example of a poker hand consisting of 5 playing cards drawn from a standard deck of 52 cards. Each card is described using 2 attributes, suit and rank, for a total of 10 predict attributes. Basically, since in poker we are always dealing 5 cards for each hand, every card is described using 2 features. One is used to describe suit and the other is used to describe the rank. There is one additional feature of basically class attribute that describes the poker hand meaning, and it describes the strength of the hand. And because of the rules of the poker, order of the cards is important as well. Basically, we can have a royal flush, only one for each suit. So we are going to use clustering for trying to solve it and analyze the data. So in poker hand dataset, as I mentioned previously, we are having 10 independent variables, 2 features for each card of the hand, and then we are having a target variable. This dataset has 2 files. The first one is pokerhandtrained.csv and the other one is pokerhandtest.csv file, and those look like something like this. So basically for each card we see that we are having the suit and rank, and as you can see, for card 1, card 2, card 3, card 4, card 5, we are having the suit and rank features, and finally we are having this poker hand result in the final column. The probabilities of getting one of these hands are represented here. So we can see here that for getting a royal flush, the probability is the smallest, and then we go to nothing, which is having the biggest probability down here. So that would be it. Now we saw what kind of poker hand dataset problem that is contained. Next, we are going to see what k-means clustering algorithm is all about. So now we are going to take a look at the k-means clustering algorithm in brief, what's it all about and how it works. Also, we are going to detect what kind of problems it solves. Also, we will take a look at something which is called the elbow method, which is used to determine the number of clusters when we are using k-means clustering algorithm. So let's start from the beginning and let's see k-means clustering. So k-means clustering is an unsupervised learning algorithm, and it will detect clusters in the data. Basically, this is a method of vector quantization that originates from signal processing, but today it is mostly used in data analysis and data mining. It aims to partition the input data into sets or clusters, that is, it minimizes within cluster sum of squares, and the short form for that is WCSS. WCSS can be represented with this formula. Basically, for every point in every cluster, you are calculating the distance from it to the center of the cluster. We will see how we find the center of the cluster later, but you sum up that for each cluster, all the distances from all the data points in the cluster to the center of the cluster, square that, and basically you do that for every cluster and sum up those values, and you are aiming to get the minimum value of within cluster sum of squares. This will be clarified shortly, but for now it's important to remember that it is actually dividing the data into certain clusters, and with that we are creating our clustering algorithm. So how does it look like? On the left hand side we are having the unclustered data, and after we apply k-means you see that it is divided into certain clusters. We are having red, green and purple cluster. So how does it work? Basically, when we start with a k-means clustering algorithm, we first choose the number of clusters, and we will see how to choose what is the best number of clusters a little bit later. But basically, once you choose the number of clusters, you just assign to the random endpoints in your data, which we call centroids, for each cluster. So we are creating a centroid for each cluster, which should represent the center of that cluster. And centroids, they do not have to be one of the data points. They can just be a point in your data space. And then you assign each data point to the closest centroid. And within that, you are forming clusters. Then you compute your new centroid for each cluster. Basically, you realize that the center of your cluster is a bit off and you move it a bit around. So you get better results. And once you do that, you reassign each point to the new cluster. Because you change the center, now you want to assign them to a new value to that new center value. And basically, then you check again if any of the data points has now been assigned to a new cluster. So if it hasn't, then your model is ready. But otherwise, you have to try to get the center or the cluster once again. So let's see how we do that. Basically, if this is our data, you can see that we cannot really see what the number of clusters is. And we say that we choose 2 clusters. So the first step you remember is choosing the number of clusters, and we are saying that the number is 2. And then we say, okay, that these are the 2 centers of our clusters. And now we have to assign each data to a certain center. And how do we do that? So we say, okay, this point is of course closer to this purple circle, and this one is closer to the green circle. So this one will be in green cluster. But the easiest way to do that is of course by finding the Euclidean distance. You can choose a different algorithm, but how do we do that? So basically we have that line between these 2 points, and then we draw a perpendicular line. And this means that these points are closer to the purple circle and these points are closer to the green circle. So this will be our first cluster and this will be our second cluster. So it will look like something like this. And then because we can see that our center is a little bit off, so we would expect our center of data to be somewhere here for this cluster. So we move those cluster points to a different place here, and we need to reassign all the data points to a new cluster center because they are looking like this. And once we move them, we do the same procedure again and taking the Euclidean distance of each data point, and we can see that some data points actually change their cluster. For example, this point was purple and now it's green. Or for example, take a look at this point. It was green and now it's purple. And if you remember, we said that if nothing has changed, our model is ready. But these points were assigned to new clusters, which means we haven't reached the center of our cluster yet. So we again need to move our centers and reassign all of them and check if we don't have any reassignments in our dataset, and then our model will be ready. So we will go back to this point and move these centers, and then you do the whole process again. You find the Euclidean distances and see if all the data points stayed in the same cluster. If they have changed the cluster, then you need to do the same process once again, or else your model is ready. But this brings us to a point where we can ask what number of clusters do we actually need to use in our k-means clustering algorithm. What is the right number of clusters that we should start with? What is the right number of clusters? And we are going to determine that using the WCSS that we saw in the beginning of this section. What are we actually looking for is the optimal minimum of this WCSS. And how do we actually get these values? Well, if we take a look at the example below, let's say that this is a final state that we got, and we decided that we are going to have two clusters. So we will calculate WCSS for this situation. Well, what we will do is we'll basically calculate the Euclidean distance for every point from this, and then we will sum them up, and we will do the same thing for the second cluster. Basically, we will calculate a Euclidean distance for every point in the cluster to its centroid, and then we will add them up to the previous results that we got from the cluster 1. And that is how we will calculate the WCSS value for two clusters. Now, if we decide to have three clusters, we will do the same thing. Basically, we will calculate the Euclidean distance for every point, that is, first cluster to its centroid, then for the second one, and finally for the third one. And we would sum that all up, and we would get our WCSS value. And as you can imagine, WCSS value would get closer to 0 with more number of clusters that we have. And basically, if we have the same number of clusters as the number of points in the dataset, the WCSS value would be 0. So, what's the point behind all of this? Well, if we calculate the WCSS value for the different number of clusters, we would end up with a graph. And you can see here that the WCSS value is biggest for one cluster, and it is as small as close to 0 for 10 number of clusters, and we are having some values in between. And the point is that we will use elbow method to determine the number of clusters that we need to have in our dataset. And the elbow method is called like that because it looks like an elbow. Basically, at this point here at 3 number of clusters, it's like our tipping point where changes in WCSS value will not be as big. So if you take a look at the WCSS value from 3 to 10, it has changed from 0 to 1000. But if you take a look at the WCSS value of one cluster to two clusters, WCSS has changed from 8000 to 3000. And from two clusters to three clusters, it has changed from 3000 to 1000. And this means that if we pick number 3 for the number of clusters for our dataset, in this example, we would not be wrong. Basically, that is the optimal value that we are looking for. So, we learned quite a lot on how to use k-means clustering algorithm, and we saw how it works, and we also saw how we can use the elbow method to determine the number of clusters that we need in our dataset. And next, we'll combine all of these together and do some feature analysis and engineering on our poker hand dataset. So, to be more exact, we will be seeing if there is any missing data, and we will also do some correlation analysis, and apart from that, we will see how distributed is the data in our dataset. So let's come to cell 1, and you can see that here I have imported all the modules and the libraries that I need. And as you can see, I imported the NumPy, Pandas, Seaborn for visualizations, and missing number for detecting missing data, and Matplotlib for plotting the data. And I also imported cdist from skippy.spatial.distance, and I also imported PCA. Now PCA will be very important for us to analyze the results, and we will see that we are actually going to squash our multidimensional data into 2 dimensions and present it that way. But more on that later. So let's start by reading our data. So in cell 2, here you can see that we have 2 datasets for the poker hand. We are having the trained dataset and we are having the test dataset. So we will import these 2 datasets from these 2 files, and then after doing that, we are going to concatenate them. But first, let's start by importing them. So I have read the CSV files using Pandas and stored the data in trained data and test data variables. And also, since our features are not having names, I have provided the column names so that the data is easier to work with. Now, in cell 3, we actually want to concatenate the trained dataset and the test dataset, because we know that in clustering we don't have test dataset, right? So now our dataset is numerical, but if you want it to look prettier, you can use these dictionaries to encode the numerical variables to categorical variables. So what I've done here is, basically I've created a poker hand map in which 0 represents nothing in hand, 1 represents one pair, 2 represents two pairs, 3 is 3 of a kind, 4th is straight, 5 is a flush, and so on and so forth. Then I have also created a suit map in which 1 represents hearts, 2 represents spades, 3 represents diamonds, and 4 represents clubs. So you feel free to uncomment this code and encode the data and see how it looks like. So then I want to concatenate my data, and thus I use the pd.concat function to combine the trained dataset and the test dataset. So now coming to cell 4, I have used the .head function to see how my data looks. And so here we can see that it's all in integers. And if you use this above encoding, you will see that these numbers are converted into categorical features. But that's for you to explore. So now let's continue, and basically I'm going to use this data, and so I'm going to check if there is any missing data in our dataset. Now for doing that, I'm going to use this missing number library, and we had imported it as MSNO. So here in cell 5, we are using that missing number library, and this plot shows us that there is no missing data in our dataset. And we kind of expected that because there will be a lot of mistakes in the game if we don't have the correct data, right? And thus there is a very less chance that data would be missing for a poker game. So thus we are not having any missing data. Now in cell 6, I have provided the code to map our data to look prettier. But I have left that exploring part to you, and feel free to uncomment this code and see how the pretty data looks like. Now coming to cell 7, let's see how our data is distributed. So as you can see here, we are making a box plot, and we are using this seaborn function to do it, and we are using our data and output of the poker hand. So basically we are looking at how our data is distributed, and as you can see, the biggest amount of results is down here between 0 and 2, which means that there is a bigger chance that we will get something from 0 to 2 than you will get a royal flush or a straight flush, which is what we expected if you have played poker. So it is actually hard to get some results like a royal flush or a straight flush, and getting 1 or 2 pairs is actually pretty easy. So that kind of explains the distribution of the data. Now in cell 8, let's do our final check. Let's do some correlation analysis. Now we don't have any correlation between these features, and after all it's a game of poker. We don't stack card 1 to be correlated with a card, but just for sake of practice, let's see if there are any correlations between these features. And we have seen this code for the heat map earlier too, and here is our correlation map. So as you can see, we expected the data not to be correlated together, and it is not. Even our heat map is telling us that nothing is going on between these features, which means that we don't need to remove anything. You can see that the darker shade is telling us that the correlations are tending towards 0. You can gather that from this color bar here on the right. So if the values are closer to 0, and as you can see these values are pretty small, so the color bar is telling us that it's around 0. So that means no correlation. So we actually don't have any outliers in this dataset also. And here we realize that we need all the data, and we don't need to remove any feature or any row for now. So we can directly proceed with the implementation of k-means clustering. So next, we are going to actually implement the k-means clustering on the poker hand dataset. So we have seen that earlier what k-means clustering is all about, and we have also analyzed the poker hand dataset and done some basic feature analysis and some feature engineering. Now we are actually going to apply the k-means clustering algorithm on our poker hand dataset. So let's jump right into it. So in cell 10, now let's apply the k-means clustering algorithm. So the first thing that we actually need to do is loop through the clusters and see how many clusters would we actually need to have. And for that, I'm using this loop here and I'm saying that our clusters are in the range from 1 to 11. So basically, I'm having 10 clusters because I'm having 10 possible results and that is the maximum number of results possible. And also I'm having this mean dist variable which will be of a type list and this will be used to record the distance. So basically this is a list and I will keep appending the distances into it. So I will basically get the WCSS value and record it. So first I'm creating a model using k-means class and then I imported that from the sklearn cluster and for the parameter I have k number of clusters. So here you can see I have done n clusters is equal to k and k will be taking the values from 1 to 11 and also I am just fitting the data into the model. So this whole data set I am fitting into our model and then I am doing the prediction. When I have done the prediction, then I am calculating the WCSS value. When I finish with this, I will be able to draw my helper method and see what number of clusters do I actually have. So this will take some time when you run it, so don't worry. It may take about 5 to 10 minutes and so let it run properly without interrupting the kernel. It will end up with the list of distances for each number of clusters. So in this array, I will have the Euclidean distance for each number of the cluster and I will get the WCSS value for each of the number of clusters. And for that, I had to import the cdist function from Skippy and you can see that how it is being used. It takes the parameters data and cluster centers. It takes as parameters the data and cluster centers that our model is having. So this is also one big feature that you need to remember about k-means class is that actually having cluster centers. And of course I'm saying here that I'm using the Euclidean distance and that is how I will calculate my WCSS values. So in cell 11, now let's plot number of clusters versus the mean distance. And here you can see what I actually get. So I'm plotting actually the number of clusters and their distances. And I'm getting this kind of graph. And you can see here that it's not a clear-cut elbow in this plot because this dataset is statistically very tricky. And as you can see here, the biggest drop that I have is when number of clusters is 2. So next, I am going to analyze the results and see how I can present this data for each number of clusters. But the important thing to remember here is that you can use k-means clustering to create your k-means model and that you can use this cdist and model.clusterCenters to calculate the WCSS value and create this kind of a graph. And this will help you pick the number of clusters that you need. In our case, that would be 2 and we will analyze the result. So now we will be using the PCA and we will use it to display the results and we will see how PCA is actually used. So we have displayed the average distance for every number of clusters and we decided that our number of clusters is in range from 1 to 11, meaning from 0 to 9. And this means that we have 10 possible values, 10 possible results, and we saw that our elbow method is not as practical for this dataset because the biggest drop that we can see is probably from 3 to 4 and I said previously that it's from 1 to 2 and we aren't sure. So we'll start with the analysis from the perspective that we have 2 number of clusters and then we will display the data and we will see how we can work with this. So now in cell 12, what I have done here is basically I have created a model for the number for 2 number of clusters and then I fit the data and I did the prediction. It's basically the same thing that I did earlier in the for loop. And also I have mentioned PCA in cell 13. And PCA is actually a method that we will use to squash our multidimensional vectors in 2 dimensions because our dataset is having 11 features. So, which would make this space 11 dimensional space. And we cannot of course even imagine that. So we will use this information to squash it, basically to map it into 2 dimensions. And that is why I have created a PCA2 and we see that this PCA class we are having 2 dimensions in it. And if we want to have 3 dimensions or 4 dimensions, we can use that as well. But for our case, we need this as 2 because that's the most efficient way to present this kind of data in 2 dimensions. Then of course, we would fit and transform our data to get some kind of plot columns, and then we will use matplotlib to display these results. So on running k-means clustering algorithm again, I am getting 2 clusters, all of our data, and then you can see that we get this result. And this can be a bit confusing because we can see here that we are having 2 clusters, but then there is this area which is mixed up, and it is not quite so obvious that what it is. But if you think about it, we have squashed multi-dimensional pictures into 2-dimensional picture. Basically, these things are mapped in that way, and we are actually having 2 clusters. And we can see here that the one over here is purple and the one over here is yellow. But PCA is quite a good algorithm for this because using it we are able to see that we are actually having 2 clusters here. Now of course in cell 15 we can use a different number of clusters. So let's rerun this, but now we will do 3 clusters. So as you can see here that I have put n clusters is equal to 3, and now I have only taken 2 dimensions for PCA. So let's see what we get. So here you can see that we are having this yellow, purple and green cluster. Of course, we are having this area in between which is smudged. But in multi-dimensional space, actually this makes sense. It actually makes sense like this too, but we can see that algorithm was able to actually create 3 clusters. So now what we can do in cell 16, we can run this on maximum number of clusters, which is 10. And then if we take a look at this data, we will see that we are having 10 clusters over here. So some are not so obvious of course, but we can take a look at our predictions here and then compare that to our data. And we'll see that they are pretty close with this. So that will be all from this section. And in this section, we explored the poker hand dataset and we saw how it looks like, and we saw that it is statistically a very tricky dataset, and we also explored what k-means clustering is and how it works. Then we applied some feature analysis on the poker hand dataset and we combined these datasets into one, and we used k-means clustering algorithm on top of the poker hand dataset. And finally, we used PCA to analyze and display the results, and we also saw how to use the elbow method. So that will be all from this lecture. Now I just want to say that the main aim of this lecture was to introduce you to a few different datasets and carry out some preliminary analysis to just get you started and familiarize you with these datasets. By no means this is a comprehensive analysis, and we were not striving to get high performance models, but rather we were just exploring how these algorithms can be applied in different situations. It would be best if you all can play with these datasets and apply all these techniques that we have learned and create a machine learning pipeline for each of these datasets. Of course, it is not mandatory to do so now, but later on, whenever you get spare time, feel free to play with these datasets and enhance your machine learning skills. Now, after your reading break, we will be moving to seeing neural networks, and in particular, we will be exploring the different machine learning frameworks that we have. So with this lecture, we have pretty much covered the concepts in supervised and unsupervised learning with the help of different algorithms. So that's it from lecture 7.